In problem 2, we want to determine the minimum sample sizes for a given margin of error. The first problem is determining the minimum sample size for a mean confidence interval. The problem part B is the same, but we're talking about a proportions problem. To get the equation for the minimum sample size, you go to my website, my teaching website, and then you click on PowerPoint 8, which I already have open. And this is the equation for the minimum sample size mean problem. And then I can go ahead and copy the equation into Excel. I'm going to go ahead and paste minimum sample size right here. Maybe paste it right there. The equation indicates that I need a z value, sigma value, and E, the desired margin of error. So I'm going to go back to my Cengage Now problem and try to determine these things. So when you read the problem, you get the standard deviation of the diameters of the bearings the machine produces is 0.09 millimeters. So I'm going to paste that right here. The desired margin of error is 0.01 millimeters. So I've pasted that value into cell B5. The next thing we need to know is the confidence level. In statistics, you generally denote the confidence level as 1 minus alpha, because alpha is the significance level. So I'm going to go back to the problem, Cengage Now problem. And in problem A, the confidence level is 95%. So I'm going to copy and paste that back into Excel. But I'm going to copy it in as a decimal, 0.95. Now, the significance level is denoted alpha. And if the confidence level, 1 minus alpha, equal 0.95, then alpha equals 0.05. And these two add up to 1. But this value here, this 0.025, that's alpha divided by 2. Why do we divide the alpha by 2? Well, the alpha divided by 2 represents the significance being split into 2 parts. Because we split the significance into 2 parts because every confidence interval has 2 parts. A lower confidence level and an upper confidence interval, or confidence level. So we always divide the alpha by 2 for confidence intervals. So the alpha divided by 2 value is 0.025. Now, where do we get the z value? We get the z value from either the standard normal table, which I've nicknamed the z table. Now, we can get the z value from this table, and all you do is you try to find 0.025, the value that is equal to alpha divided by 2. So you find 0.025. 0.025, let me blow that up. 0.025 is in row negative 1.9 and column 06. So the z value would be 1.96. An easier way to find the critical values for a confidence interval is to go to the infinity row of the t table. These values down here are z values. The values up here are t values. So we can go to the t table in the infinity row and find the z values that correspond to a tail probability, or in this case, alpha divided by 2 would be 0.025. So notice that when we're in column 0.025, the value in the infinity row is equal to 1.96, 0. So this gives us 3 decimal place accuracy. whereas the standard normal table only gives us 2 decimal place accuracy. I'm going to type in here, or copy in here, 1.960. Now we're ready to calculate the minimum sample size that is needed. Okay, so the minimum sample size that is needed to ensure a margin of error of 0.01 is equal to the z-value squared times our sigma squared divided by the margin of error squared. Now, this rarely gives an integer. So we either need to use 311 or 312. So which do we use? Do we use 311 or do we use 312? Well, to answer that question, we have to go back to the expression for the confidence interval. For 1 minus alpha confidence interval, we have the sample mean plus or minus the z-value, which is multiplied by the standard error. The standard error is the standard deviation divided by the square root of n. So this right here, the z times the standard error is the margin of error. I'm going to go ahead and copy that into Excel. Now remember from your algebra class, as n gets smaller, the standard error will get bigger, the margin error will get bigger. If we use a bigger n, the standard error will be smaller, the margin of error will be smaller. We always round this calculation for n up to the nearest integer. If we use 312, then we're going to have a margin of error less than 0.0. We copy that into the answer blank. Now in part B, we have a similar question, but now we're talking about a proportion. And this preliminary poll reveals that 46% or 0.46 of 50 voters support a presidential candidate. At 95% confidence, how large a sample is needed to obtain a margin of error of 4 percentage points? So our margin of error is 0.04. When determining the minimum sample size for a proportions problem, the equation is a little different. You have your z-value that is squared multiplied by p times 1 minus p. In a proportions problem, p times 1 minus p can be thought of as sigma squared. And you divide that by the desired margin of error squared. In the proportions problem, the confidence level is 0.95. The alpha level is 0.05. Alpha divided by 2 is 0.025. And the z-value is 1.96. That is identical to what we had before in part A. The preliminary proportion is 0.46. And the desired margin of error is 4 percentage points. We enter them into the Excel spreadsheet. So 4 percentage points is the desired margin of error. The preliminary proportion is 0.46. Now we have everything we need to compute the minimum sample size. In the minimum sample size, we take p star times 1 minus p star. And you can think of that right there as sigma squared for proportions problem. P star times 1 minus p star is 0.2484. Now we compute the minimum sample size. We square 1.96. We multiply that by p star times 1 minus p star, and then divide that by the desired margin of error squared. So we have z squared times p times 1 minus p divided by margin of error squared. Then we round that up to the nearest integer, 597. Copy and paste that into Cengage now. Check my work. And we get both of the problems correct.